Okay, thank you very much. So this is work with Julia, who is right here, and Simon Caranuo and Miguel Solon. So the starting point is this very general big problem, which is, well, it has been mentioned already many times here, which is this bound state problem in QFT. So this problem is relevant for many systems, starting from the proton, from atoms to black holes. And this problem is difficult in QFT because in QFT we are very used to computing S matrix. And the S matrix involves scattering of objects that are very far away. They come together, they scatter to infinity. And these bound states are just particles just together all the time, right? But the S matrix is quite special, right? The S matrix has very special properties in the complex plane. And in particular, we believe that for those states that scatter and can form bound states, the information about these bound states is encoded in the S matrix, and in particular shows up as singularities in the S matrix. And I think we can classify the singularities of S matrix in two main categories. We have Landau singularities, which are kinematic singularities. They are there for any QFT. They follow from basic principles. And in particular, they show up in individual Feynman diagrams. So I'm going to take this opportunity to advertise this package that I wrote with Mathieu Giroux and Sebastian Misera. So this package computes Landau singularities, and I think it could be very useful for many people here. But today, I'm interested in these bound states. In particular, these bound states are dynamical. They depend on the coupling. They depend on the theory. In general, they are non-perturbative. And to see them, you need to resum many diagrams. So let me give you an example. Well, this is the canonical example, which is the hydrogen atom. And in this regime, we know exactly the class of diagrams. These have showed up already in previous talk. So the first diagram, of course, is this Coulomb interaction. So it's just give you the 1/T pole that we know very well. The next diagram is just the box, gives you a logarithm. And then you keep going. And then this beautifully resums into these gamma functions. And the gamma functions have poles at negative integers. And these poles precisely correspond to these bound states of, well, these energy levels of hydrogen. So in the end, we end up with a function which has these very beautiful properties. For positive energies, it has a branch cup. This is the simplest Landau singularity. For negative energies, it has these bound states which depend on the coupling. And the problem in QFT is that we have a lot of diagrams. They are very complicated. At this point, second day of the conference, we are all convinced that it's very hard to compute these diagrams. So how to deal with this problem in general? So there are many ways. One way that is particularly relevant for gravity and has been rediscovered in this context is this effective one-body approach. And this was proposed by Todorov in 1971, and it was inspired this very well-known work in GR by Bonanno and Damour. And the idea is very simple. The idea is that I can treat these two bodies that are scattering as effectively one body. And I can write down some Schrödinger equation whose eigenvalue depends very non-linearly on the energies. And this captures all these kind of relativistic corrections. And then this potential shows up here. And we can, in practice, solve this equation by extracting the amplitude, and then you find some Born series, and you compute this amplitude by iterating this potential. And the main idea is that by choosing this particular f, when you take this Born series and you take a two-particle cut, you see that you obey QFT principle, and moreover, the potential is real across this cut. Okay, so in general, so the main idea is that on one side you have Feynman diagrams, on the other side you have this Born series, and so by matching this EFT, you can extract this potential, you reinsert into this equation, and this allows you to compute stuff about bound states. And so there are many applications of this. So the first one, which was the historical one, is that allows you to compute corrections to the spectrum of hydrogen. So I'm going to give a very simple example in this case. But this actually has been, it was rediscovered in this paper. And then, well, applied in many other contexts. In particular, if you take the WKB approximation of this equation, you recover this amplitude action relation. And when people mean action, what they mean is the action of this effective one body. But there is a last application, which is where most of our results are, these new results, which is the application of these ideas to this so-called Born regime, where we are interested on scattering a wave on a background. So this is what I'm going to try to get to. Okay, so I mentioned a lot of regimes here. So let me show you a table which captures all of these different regimes. So we start by these scales that I show here. So this is true for any theory, right? So the first one is impact parameter. So it's given by this B. We have the Broglie wavelength, that is a length scale in quantum mechanics. We have the quantum wavelength, which appears in QFT. So by taking different relations by these scales, we can reach all of these regimes. So in particular, if I scatter two massive bodies and I take the B to be the largest scale, then I'm just describing the iconal regime. If I take B of the order of the Broglie wavelength, much larger than the Compton, this is just quantum mechanics. If I take scattering of a massless particle, I'm just scattering a wave on a background. And so the idea of the talk is just to cycle through these regimes. I'll show you an example and finally end up on these new results, which will happen here. Okay, so I'm going to start by just deriving Kepler's law from this idea of continuation. So the idea is exactly like in the previous case. I scatter two masses in the Newtonian regime. If I take this partial wave basis, this just resums to a set of gamma functions. And these gamma functions have the poles, as I mentioned before, which are these bound states for negative energy. And now the idea is that I want to describe the classical scattering or the classical in-spiral of these objects. So I take the classical limit. This object exponentiates to this radial action, which has been mentioned many times here. But the reason why I'm showing you this, well, the reason why I'm also excited about this is because in this case, we can explicitly compute this function. And, well, we can play with it, right? So the time delay, you just get it by just taking derivatives of this. And so it gives you the very well-known result in gravity that the time delay just scales with the log of the impact, well, the distance between the bodies. But now the question is, what happens to these bound states? We know that in classical physics, there is no such quantization. What happens is that these bound states actually condense to form a branch cut. And the branch cut you can already see in this function, because the branch cut is precisely the branch cuts of this log. So when you take the argument to be negative, it gives you exactly the position of this branch cut. In particular, the branch point is the lowest allowed circular orbit. Well, it's a circular orbit, so it gives you precisely the energy for that. And as you increase energy, this orbit becomes more elliptic, eventually breaks down, becomes a paraboloid in this part. And now, like after I continue to this regime, I just pick up the monodromy of this log, and so I just take the derivative, and I'm able to compute the period, and this is exactly Kepler's law. So, and the nice thing is that you see the relation between the time delay and the period is that the time delay depends on the log, the period depends on pi. So these are very well related because they come from the same function. Okay, so this was just a very simple example. So now let me go show you one example in this regime. Okay, so now I'm gonna consider this so-called Born regime, and in particular, I want to describe QED corrections to spectrum. In particular, I'm going to focus on this cute example, which is the example of a bound state of an electron and a positron. So now we have way more diagrams, right? So we no longer have just a simple exchange, we no longer have the ladder, but now we have this diagram here, which corresponds to the vertex correction. We have this vacuum polarization diagram. We also have this diagram here that does not exist for the case of hydrogen. And this diagram here corresponds to the just intermediate production of photons. And now we just match this picture, as I showed before. Clearly, this just corresponds to an iteration of the potential. So everything else should be grouped into the potential. Once we have the potential, we can just compute corrections to bound states. So then what happens in particular, what is quite interesting is that this gives some imaginary part. In this non-relativistic regime, is just a log. So it gives you some I pi. And then this, from this connection to the Schrodinger equation, you can just compute the imaginary part. So you see that the potential acquires some imaginary part, and you just compute the correction to the energy levels, which now will be the decay rate by integrating against the wave function. So you plug the wave function, it just gives you a result which agrees quite well with the experiment. Okay, so this ends my kind of pedagogical kind of examples. So far, we've been using this connection to take the Feynman diagram expansion and extract some potential. Now we're going to turn the logic around. I'm going to find some wave equation where I can extract some potential, and from that, I'm going to get the amplitude. And this is just the simplest, this is the original approach, right? In quantum mechanics, you write a wave equation, you get the potential, you compute the Born amplitude, you get the amplitude. And we were quite surprised that such a simple idea was not being, or at least was not very, at least we couldn't find it anywhere. So we're going to apply it in some examples here. So what I'm interested here is the example where I'm scattering a massless wave on a background. So to be specific, I take some action of some scalar field on a Schwarzschild background. I derive the equation of motion. It will be this wave equation. I write it in this Schrodinger form. I extract some potential, which at 3 level is just the 1/r potential. And from that, I get the amplitude is just a Fourier transform. So it just gives me the 1/t pole. Right? This is a very simple example. And now we're going to try to do this in Kerr. So we're going to try to do exactly the same thing, but now in the Kerr background. And now things get quite complicated. So I think everyone working on Kerr is very brave. That's what I learned from this, trying to do this. So in a Kerr background, we have another vector. So we have the spin vector. And we try to write the Teokolsky equation exactly in this form. And we use Kerr-Child coordinates because it allows to make everything kind of covariant. So when you write it in this form, the potential looks like this simple expression. And so this is, so the role that we have to do if we want to do the same thing as I did before, we need to take the Fourier transform of this. So let me not tell you how we did it, but you can do it. And this is the answer. It actually becomes quite simple in the on-shell. So the first line is this iconal Kerr-Compton, which was first proposed in these papers and many others that followed. So it exhibits this very nice exponentiation of the spin. But then we also find a surprise, which is the presence of contact terms. And even though they don't look like that, if you expand in Q, you see that all these cancels give you really contact pieces. And this is quite surprising in a way because you see the potential is all long distance, yet it gives you contact terms. And so this expression satisfies crossing, SU crossing. It's analytic. It has no spurious poles. It factorizes as the right iconal limit, and it's derived from GR. So as far as I know, this is the only, as far as I know in the literature, this is the only answer that satisfies all these properties. So we can do the same exercise for the photon. And for the photon, there's a similar potential, which now depends on the polarizations, but you can still do a Fourier transform, and it gives you this huge expression. But this huge expression satisfies all these other properties, but it also is gauge invariant. And gauge invariance is actually quite non-trivial to satisfy because it relates all these terms that are contact terms, relates to terms that are relevant in the iconal limit. So we still think that this object is still probably the simplest object that can satisfy all these properties in a way. Okay, so I think it would be very nice to try to match these to like these word lines that people have talked before in other talks. But okay, So now I want to move on, and I want to describe what happens at loop level. So far I just considered the three-level scattering of a curved background, let's say. What happens if you go to loops, if you start iterating this potential in the Born series? And because it's very complicated, as you could see already at tree-level, we're just going to stick to Schwarzschild, okay, where things are also complicated. In particular, you find that this diagram, these loops become UV divergence. You need to introduce counter terms, which are called love numbers. So let me tell you a bit about love numbers. So here I just show a bunch of astronomical objects. And the love number, the idea of the love number is just it parameterizes the deviation from point particle. So it tells you basically how much a body reacts to a tidal field. So if it's very rigid, the love number is small. If it's malleable, the love number gets bigger. So for the moon, which is very rocky, the static love number is zero. Well, it's almost zero, it's very small. And then as you increase, you add an ocean. In the case of the Earth, it gets bigger. You add gas all around, it even gets bigger. And the love number, the measurement of love number is actually tied to this old question of is there life outside of the Earth? In particular to Europa, which is a moon of Jupiter. And you see the love number is quite close to the Earth one. And this is one of the main indications that Europa, even though it's icy, it's believed to have an ocean inside. So actually there is an ongoing spacecraft that passed Mars, is on its way to Jupiter. And its main goal will be to measure the gravitational tidal love number, which will be an independent diagnostic of the presence of this ocean. And actually I put here a poster of a movie, it's a sci-fi movie where they explore the possibility of life in Europa. And well, this movie is quite interesting, but I think you shouldn't watch it alone. You should watch it with someone else. It's very, but yeah. Anyway, so we can actually be a bit more rigorous, okay? So we can define love numbers very nicely in a EFT as a Wilson coefficient of a wordline action. And this is what will be the difference between all these compact objects, including black holes, planets, yeah. So the idea here will be to scatter a scalar wave on a compact object in this long wavelength limit. So there will be two terms, there will be two pieces, right? There will be a long distance force coming from gravity. These we can get by expanding the metric in G. And then there will be these contact terms, which will be the love numbers. So in terms of diagrams, this answer, because we are in the probe limit, this potential resums all these type of fan diagrams. And these love numbers will just be these contact-like diagrams. So now we use this connection between the potential and the wave equation. So we can write down some sort of effective wave equation for the scattering of a wave on any compact object, where now this potential will be the sum of these two pieces. So it will be the gravity potential and also the contact potential. And to get the amplitude, we're going to solve the Born series for this potential. So this Born series that I showed here. So we're just going to solve these integrals. And it turns out that these integrals can be solved exactly. And we know that the family of integrals is always HPLs. So this allows us to automatize these to very high orders. So we're able to push the state of the art very, very far. Okay, so let me give you our results. So this is the phase shift at order G7. And you see that, I mean, these are very long expressions, very big numbers. But you see that the first UV divergence shows up here at G cubed. So this is so for this answer we match with this paper, and the rest is new. So yeah, so in this paper I should say this was very important because this paper computed this by computing actually the loops in Feynman diagrams. We use this Born series approach, which in the end amounts to a 6-loop computation. Yeah. Okay, so this is just the EFT result without love numbers. So to cure this UV divergence, we need to add the love numbers. And by adding the love numbers, then we can renormalize these divergences and match them to GR. And for example, to get the black hole love numbers, we find after matching, we find these results. So up to G cube, we match with this paper, and then we have new results beyond G cubed. And in particular, you see that there is some zero love numbers, and these are the well-known static love numbers of black holes that should be zero. And because these love numbers they eventually run, you can compute some RGEs. And so this is what we have toward the G7. And the nice thing, or the surprise, was the presence of this quadratic term in the equation. And we thought, I mean, as far as we know, we didn't find it anywhere. So this is quite interesting, because if you solve this equation, you see that it gives you some sort of geometric series, which is expected from a Born series. Okay, so let me conclude. So I hope to have convinced you that this EOB equation is a tool, is a very nice tool for gravity. So we propose some scalar and photon Kerr-Compton amplitudes, and we predicted some Schwarzschild love numbers to order G7. So in the future, we are interested, of course, in getting the relevant case where we are scattering gravitons on Kerr. So we are doing this with Simon and Julia. We're also interested in the general properties of these S matrices involving scattering on black holes. In particular, we find some very interesting relations between causality and IR effects. So this is work with two students at UCLA, Tushar and Anna. And finally, well, I started the talk talking about these bound states. And in general, these bound states can be unstable. And in fact, most particles that we know are unstable. And we assume many times that these unstable particles, well, they respect the same properties as stable ones. So yeah, so this is something we are trying to understand, if we can make all of these properties more rigorous. So this is with Aditya Embar and Selina Pashenchnik, which I think is somewhere here in the audience. So yeah, with that, let me conclude. Thanks. Yeah.